Let's look now at the effect of fuel moisture in the combustion process. So we start with dry fuel, zero water. It doesn't mean that there is no water in dry wood. There is always some water bounded in the wood itself. And of course, when you have the equation for combustion of wood in air, there is always a little bit moisture that is used in the process, and there is always a little bit of the equation that includes the water component. But now if you decide to use 100% of fuel moisture, it means the same amount of water as dry fuel, you go from 0 to 1 in this cell. In this case, what you did, you changed the equation of combustion. Before you had 25 grams of fuel, and if you have the 0 there, you would have 2 grams. The 25 grams of fuel would combine with 2 grams of water, bounded water. If you have a ratio of 1, it means the same amount of water in the fuel as dry mass. You have 25 grams of fuel that are combined with 25 grams of water, and this is the equation that will develop with the combustion of that moist wood. In this case, when you look at what happened to the heat of combustion, the heat of combustion, the maximum value is still the same, but what you changed here was the total heat of pre-ignition, 3.7. It indicates that there is a good amount of energy that is required to ignite the wood. And so the difference between these two values, 17.1 and 3.7, is the adjusted heat yield, 13.4 kilojoules per gram of fuel. So it means that you reduced by 20% the heat released of this fuel by increasing fuel moisture. And this is very significant, and it has lots of effects in the processes that are related with fire. So again, if you now go back to 0, absolutely dry fuel, what you see is that the total heat of pre-ignition is reduced substantially. It's only 0.6 kilojoules per gram, and the adjusted heat yield, 16.5, is very close to the maximum heat of combustion that is possible to be released by this fuel when it's dry. You can express heat of combustion in different ways. Here, in this equation, in this spreadsheet, you have the equation for combustion in air of wood as expressed by this chemical composition and this low heat of combustion as it was given in literature. And by doing that, you can then start looking in the spreadsheet where in the bottom of the spreadsheet how this heat of combustion can be expressed. So we saw before that the heat of combustion could be expressed by grams of fuel. So in this case, 17.1 kilojoules per gram of fuel. And we saw also that the total heat of pre-ignition could be estimated as 0.6 kilojoules per gram. Now we can see also that using this equation of combustion, you can also express the heat of combustion not only per grams of dry fuel, but also per grams of oxygen used. So in this case, you have 12.6 kilojoules of heat released per each gram of oxygen. You could also express the same thing, the same heat release per grams of air, because you know how what is the composition of air. So in this case, it's 2.9 kilojoules per gram of air. And here also you can have the ratio of oxygen fuel. So it means here that by using this equation, you can understand that you need 1.4 grams of oxygen per gram of fuel consumed. And this is going to be extremely important for other explorations of this same equation.